What's up, Jack? Welcome to our presentation. For our project, we decided to look at the topographical map of Mount Rushmore. So why did we choose this map? Well, to start off, we decided to look at it for its varied elevations. We knew for this project we wanted to analyze a map or an area that had many different heights so that we could observe and analyze different contour lines and making it ideal for analyzing partial derivatives and slopes at different points. This brings me to our second reason. We decided to observe a landscape that had all these varied heights to sort of give us a challenge to work with in this final project. However, aside from these reasons, we also look at this terrain because of its practical application. Over time, with natural forces like wind, water, and temperature, the mountain slowly eroded. And the concepts of partial derivatives and directional derivatives can tell us more of how the elevation at specific points on the mountain decreases due to this erosion. And so, with this project, we hope to uncover things in this historical landscape using the mathematical concepts we learned in class. So let's get started. How did we decide what bounds to work with?
Alright, so this is Mount Rushmore. We decided to choose this boundary being a rectangle. Firstly, because it includes an easy minimum, it includes a maximum, and then it's 3,000 feet long, 1,500 feet tall. And then within this boundary, we decided to choose a point at the minimum, at the maximum, the summit, one where the faces are, and then another just on the backside for good measure, showing just a random place on the mountain with a steep slope.
Okay, and using math, we calculated some derivatives for our project. So we did partial x derivative using our limit that we knew from class and our y derivative. And this was important because it allowed us to calculate close together points to get an instantaneous rate of change. And then from there we got our gradient, which is just the partial x and the partial y. And then from there we were able to get a directional derivative because we calculated it with a unit vector. And with that information we were able to get our tangent plane using our partial derivatives. So in application, what does this look like? Let's look at an example with point W.
At point W, we found a partial x derivative of 0.235 feet per feet and a y partial derivative of 0.214 feet per feet, which means the gradient would be 0.235 comma 0.214. And then using that, we can find the tangent plane equation as such. And then we're also able, using the gradient and the unit vector going towards our peak, to find that our directional derivative is equal to negative 0.2876.
What about the rest of the map? Let's look at some critical points like max, mins, and saddle points.
So some of our critical points, so we have a local max right here by the 680 contour line, and basically the hills that we see should be local maxes, and the W point that we chose is a local min, and there's some saddle points which are it's like a point in between two of these hills that we see, so this one would be the saddle point, and also this one would be a saddle point right here. And, yeah.
Finally, let's take a look at our visual.
What's up, Jack? This is our physical model. It represents a small section of our topographical map. This is the section it represents. Yeah. As you can see, it perfectly matches up pixel for pixel with our topographical map. We have some level curves marked out and some points. We're gonna take a look at that. Yeah, so this is our point O, which you can see right here. This is our point P, which you can see right here. And we have level curves 5640, 5600, 5480, 5440, and 5400 marked out on our model. And lastly, we have the boys on our physical model. So
keep that in mind for creativity.
Hey Jack, we just want to say thank you for the great semester. It's been a good time. Thank you for having us do a fun final project instead of something really lame and boring.